In this video, we're going to talk about section 4.6, which is on optimization. Optimization is a class of application problems that involve finding the maximum or minimum of something. Now, this is something we spent a lot of time with in chapter 4 so far. However, it's either had no context or only been in the context of drawing the graph of some function. So now let's look at it in a real world context. Like with this example. A carpenter plans to make an open-top box from a 24-inch by 45-inch metal sheet by cutting congruent squares from its corners and folding up the resulting flaps. What are the dimensions of the largest box that they could make? I like to start all of these problems, just like my related rates problems, by drawing a picture. Here you can see I've got some sheet of metal that is 24 inches by 45 inches. And I'm going to cut these squares out of the side. So that they're all the same, and that will give me a flap on each side of the sheet that I can fold up to make a box. And the goal here is to maximize the volume of that box. This is the problem in English, but let's look at what that problem means in math. We know that the volume of a box, or a rectangular prism if you want to sound fancy, is length times width times height. And we could also maybe rewrite that goal in a more mathematical way, because we know that the maximum is going to occur at a critical point. So maybe the math goal of this problem is to find all the critical points of V. But there's a pretty glaring issue staring us in the face, and that is that V is a function of multiple variables, right? It depends on the length, width, and height. And that's a big problem, and we won't know how to address multivariate functions until Calc 3. So maybe there's a different way that we could write this function out in terms of only a single variable. We call this context from the problem that's going to help us do that a constraint. The constraint for this problem is that there's only so much metal to work with, right? So notice when I cut out a corner, that cut is the only aspect of this problem I really have control over. I'm going to give that cut length a name, x, right? So we're going to let x be the side length of that square cut out. Now, when I fold the box up, you'll notice I get this picture. The height of my box is actually just x. And in fact, both the width and the length depend on x as well. For example, for the width, I'm starting from 24 inches of material, and then I'm making a cut with length x from both sides. So the width of my box is 24 inches minus the two cuts, or 2x. Same thing for the length. I start from 45 inches of material, and then I cut x out of each side. So the total length is 45 minus the two cuts. Now that I have used my constraints to write each variable in my volume function in terms of the same variable x, I can rewrite my volume function as a function of only x. That is 45 minus 2x, or length, times width, times height. When I distribute all of that out, I end up with 4x cubed minus 138x squared plus 1080x. Remember, the goal of our problem was to find the critical points of this function. I would encourage you to pause the video here and see if you can do that on your own. Remember, critical points are either where the derivative is 0 or where the derivative doesn't exist. The derivative of this function is 12x squared minus 276x plus 1080. That's a polynomial, so luckily there's no critical points that cause the function not to exist. However, that function does have zeros. Notice this factors nicely into 12 times x minus 18 times x minus 5. So 5 and 18 are the critical points of this function. However, one of those maybe shouldn't sit super well with you. In the math world, the domain of this function is all real numbers. But in the real world, there's only so much material I have to work with. Making an 18-inch cut wouldn't make any sense because I only have a 24-inch wide piece of metal, and that would require me to have 36 inches of material to work with, and I just don't have it. The largest cut I could possibly make would be 12 inches on each side, and even then that would be leaving me with 0 width. So the real world domain of our problem is the closed bounded interval from 0 to 12. I use those words closed and bounded to hopefully remind you of the extreme value theorem. The extreme value theorem tells us that the absolute max and mins for a continuous differentiable function are both attained on closed bounded intervals. So now I have a short list of points to check. The endpoints of my closed bounded interval, 0 and 12, and the critical points that fall within that interval. In this case, just 5. When I plug those into my function, I find that v of 0 is 0, v of 5 is 2450, and v of 12 is also 0. So the absolute maximal volume of this box is 2,450 cubic inches. Now, careful, because this isn't actually what the problem asked us to produce. The problem asked us for the dimensions that produce the maximal box. So we find length, width, and height to be 35 inches by 14 inches by 5 inches. Let's try a somewhat more challenging problem. The city plans to build a rectangular playground on a right triangular plot with lateral sides 4 meters by 12 meters. What are the dimensions of the largest playground that could be built? I'd encourage you to pause the video here and see if you can draw a picture and state the goal for this problem on your own. Hopefully, you were able to produce this picture. I've got a right triangular plot drawn in green, and I'm trying to fit a rectangular playground drawn in red inside of it. And the goal is to maximize the area of this playground. Hopefully, we all recall the area of a rectangle to be length times width. Can you think of a way to think outside the box on what constraint do we have that could allow us to write the area in terms of only one of these variables, not two? Well, notice the little triangle at the top is similar to the full triangular plot, since they have all of the same interior angles. That allows us to write vertical side is to vertical side as horizontal side is to horizontal side. That is, 4 minus w is to 4 as L is to 12. We can rewrite this constraint as L equals 3 times 4 minus w. Technically, nothing is stopping us from solving for w instead and writing our area in terms of length. At this point, that's totally up to you. For me, I think it's just a little bit easier numbers to work with when you solve for L instead of w in this problem. So now I can rewrite my area function as length times width, which simplifies to 12w minus 3w squared. Pause the video here and see if you can find both the critical points of this function and the real-world domain. Hopefully, we were able to arrive that 2 is the only critical point. The derivative of this function is 12 minus 6w, and when I set that equal to 0, I get w equals 2. Notice there are no critical points that cause a prime to not exist, since a prime is a polynomial. That said, its domain in the math world is all real numbers. However, it wouldn't make sense for us to have a negative width, surely, and it also wouldn't make sense for our width to be more than 4, since we don't have that much available on our lot. So the real world domain for this problem is the closed bounded interval from 0 to 4. Next, see if you can find the maximal area on your own. Check this short list of points, the endpoints, and all the critical points that fall within it, and find the maximal function value. Hopefully, we were all able to conclude that a of 0 is 0, a of 2 was 24, and a of 4 is 0, meaning that the maximal area for our future playground is 24 square meters. Let's summarize these two problems and see if we can't come up with a step-by-step list to help us solve future optimization problems. Because similarly to related rates problems, each problem is going to look slightly different, have different constraints, and different real world scenarios, right? So no two optimization problems will look identical. Again, a good place to start is by drawing a picture. This helps me to wrap my head around what's really going on in the situation. Next, you should state your goal and find a formula for the quantity to be optimized. Oftentimes, this initial formula is going to depend on multiple variables, and you won't be able to find the critical points outright. So, we move on to step 3, which is using the constraints from the problem to rewrite that function in terms of only a single variable. Sometimes, like in the playground problem, I can rewrite one of my variables in terms of the other. But other times, like in the box problem we did, I might need to write all of my variables in terms of some new thing entirely. Next, we need to find the real world domain of our problem so that we can build our short list of points to check. Finally, use the extreme value theorem to find the optimum. Again, this is just sort of the fancy language for plug in your endpoints and your critical points, see which one gives you the biggest or the smallest if that's what you happen to be looking for. This is going to be the end of the video, but I am going to upload a few more examples in my notes to Blackboard to go along with this so that you have some extra help.